We're now going to take a look at the last general group of trigonometric integrals. And this group of integrals involves powers of tangent and secant, right? Now, previously, we did a lot of work to derive this reduction formula for powers of secant, and one of the types of integrals that we're going to look at today will require us to use that formula, right? So it's not always going to be needed, but there are some instances when we will have to use that reduction of order formula, right? And that was covered in a previous video. So what are the integrals? What are we interested in now? We are now interested in powers of tangent and secant. Right? Right? And very similar to what happened with powers of sine and cosine, depending on whether m is even or odd or n is even or odd, there is a very specific procedure that we will apply, right? So let's go through the three cases that we're going to look at. So suppose n is even, right? So the first case is when n is an even number, right? Well, here is the process, right? First thing what we're going to do is to, if n is an even number, we will be able to split off a factor of secant squared, right? So we're going to split off or factor off, right? A factor of secant squared, right? And that factor is going to enable us to do a u sub towards the end of the process, right? In order to do this u sub, we're going to apply the identity. So apply, and the identity that we're going to use is that secant squared, right, can be written as tangent squared plus 1, right? So we're going to keep this factor off, and if we have other powers of secant, or we should say like secant squared, we're going to write it in terms of tangent squared. And because of that, then the third step will be a possibility, and we're going to make the substitution, right? So again, we're going to turn this into a regular u sub problem, and the substitution that we're going to make in this case is to let u be equal to the tangent of x, all right? So it's not until you actually see these procedures in practice that you really get what they're talking about, all right? So let's do an example of this one. So let's say we have, I don't know, the cube root of tangent of 2x, right? And then what we're going to have here is secant to the fourth power of 2x dx, all right? Okay, so here is our integral. And again, the only thing we're going to look at now is say, yep, I see an even power of secant, right? So secant to the fourth power. So then this procedure will apply, right? So the first thing I'm going to do is to write this as secant squared of 2x times secant squared of 2x. So essentially write this to split this one factor, or one factor into two factors that look like this. Right? So we got our cube root there. And then this can be written as secant squared of 2x times secant squared of 2x dx. So this is that factor, right? The secant squared that's going to allow us to make a u sub, right? But in order for this u sub to work, I want the remaining terms or factors in the integrand to be in terms of tangent. This one is already in terms of tangent. I need to convert this one into an expression that's in terms of tangent. And that's where this identity comes in, right? Now, this identity, like all the other identities, can be thought of as in a more general sense. So here's kind of the general way of looking at this identity. If I have secant squared of some quantity, some expression, and this can always be written as tangent squared of that same expression plus 1. So if the problem has a 2x here inside the secant squared, well, when I apply the identity, like so if there's a 2x here, there's going to be a 2x there, right? So let's go ahead and do that, right? So again, we're going to rewrite this factor in terms of tangent squared. We're going to keep the other factor separate and apart, right? We're not going to touch this right now because this is going to end up being our ticket to our u sub, right? So let's do this. And let me go ahead and write this to the power 1/3 because I have a feeling that at some point we're going to need to do that. Just a hunch, right? So we got our 1/3 power there. Now secant squared of 2x, that is the quantity tangent squared of 2x plus 1, right? And then I'm going to keep this factor here, the secant squared of 2x dx, right? Again, when we use these procedures that involve splitting off one factor and then rewriting the separate another factor, it just looks like we're making the problem more complicated. But the important thing now is these two factors are in terms of tangent, right? Tangent of 2x. And this other factor here is the derivative, or it's close to the derivative of the tangent of 2x. So that's why I can make my substitution, right? So the substitution here, I'm not going to use tangent of x because in the problem there is a 2x, right? So again, this is just kind of a base result. If I have tangent of some other quantity, right, and then secant squared of that same quantity, then the u from my u substitution will be the tangent of 2x. Because when I differentiate this, here's my du. Because of the chain rule, I end up having 2 secant squared of 2x dx, right? So what do we end up with? So I will be able to replace this one, and in a second I'll write down what the replacement is, and then I'll be able to replace this and also this. All right? So what is the replacement for secant squared of 2x dx? Well, divide this equation by 2. So I'll have 1/2 du is secant squared of 2x dx, right? So that's what we have. So this differential here becomes 1/2 du. This tangent squared becomes u squared, and then this tangent to the tangent of 2x to the 1/3 becomes u to the 1/3. So again, and we've seen this before, where we end up having, when we do our procedure, we end up replacing this trigonometric integral with just essentially an integral of power functions. Right? So let's write it down carefully and then evaluate. So we have the integral, so this is the u to the 1/3 times the quantity u squared plus 1, and then times 1/2 du. So now factor out that 1/2. And inside, before we integrate, we have to distribute the u to the 1/3 there and the u to the 1/3 there. So by adding those two powers, I'll end up with u to the 7/3, right? And then plus u to the 1/3. And now we really see the benefit of doing this procedure, because now we get to use our basic power rule for antiderivatives, right? We couldn't use it previously because the power rule works only for powers of x, right? Or in this case, powers of u, right? It doesn't work in general for powers of other functions like powers of logarithms or trigonometric functions, right? So now let's apply that power rule. So we have 1/2. Adding 1 to this gives us a power of 10/3, and then dividing by 10/3 is the same as multiplying by 3/10. Right? Adding 1 to this gives us 4/3, and then dividing by 4/3 gives us 3/4. And then we have u to the 4/3, and then our plus c, right? So distribute the 1/2. That gives us 3/20. And then why not reverse the substitution all in one? So then we have replace the u with the tangent of 2x. And I'm just going to write it exactly in terms of the order of operations, the way you would evaluate it. So we have that. Oh, not 4/3. That one's 10/3. Right, so we have 10/3 there. And then plus, again, distribute the 1/2. So we have 3/8, and then another tangent of 2x. And then that one's to the 4/3. And then that's plus c. Now, since the original integrand was in terms of roots, if you wanted to rewrite this so that we were using radicals, this is what it would look like. 3/20, and then this would be the cube root of tangent of 2x to the 10th power, right? Which could be written like that. And then plus 3/8 times another cube root, and then that's now of the cube root of tangent of 2x to the 4th power, which we can write like this. All right, and then our plus c. So that's our antiderivative, right? So if we have an even power of secant squared, right, we can factor it off so that we have our secant squared dx. That's always going to be our differential. Why is it always the case? Because we're always going to rewrite it in such a way that we're always going to choose u as the tangent function, right? And the derivative of tangent, well, that's always secant squared. Now, if we have to use our chain rule, we have to be careful if we have additional constants. But again, we know how to handle additional constants. All right? Okay, so that's our first procedure. Let's look at the next case. The next case now is when m is an odd number, right? So when m is odd, right? And just so that I don't have to scroll back up, let me write down again what I used as kind of the general form of these integrals. Right, so now we're saying, what if the power of tangent is odd? Well, we're going to do a similar procedure, but this is the type of factor that we're going to split off. So let's split off a factor of secant times tangent, right? And you might remember this comes up in Calc 1 as the derivative of secant x. So that kind of gives you a clue as to what our u is going to be, right? But in order for that to work, this is the identity that we have to apply. So we're going to apply the identity, and what we're going to do is replace all the tangent squareds, right, with secant squared minus 1. So it's basically just taking the identity that we used in the first procedure and solving that identity for tangent squared, right? And then we're going to use the substitution u equals secant x. And that's why having the secant x tangent x times my dx, that's why that differential works, right? Let me write this down more clearly. All right, so we have that, right, so that's going to be our u, all right? All right, well, let's take an example. Let's take a look at this one. Let's look at something like the integral of tangent cubed times secant cubed, right? So let's take a look at this one. So tangent cubed times secant cubed dx, all right? Okay, so we can see there we have an odd power of tangent. So here's our process. We're going to factor off one of the secants and one of the tangents. And that's going to, again, make it look a little bit, maybe scarier than it really is. Right? But let's do, so this will be tangent squared x, secant squared x. And again, the reason why these powers have gone down by 1 is because I'm going to write, in fact, let me do it in the specific order that it states. The order doesn't matter because everything is multiplying, but there is the additional factor of secant, and then there is the additional factor of tangent. All right? And again, this is going to become the du in our problem. But in order for this to work, I need to rewrite this factor so that it is in terms of secant squared. And that's where this identity comes in, right? So replace the tangent squared with secant squared minus 1. So it looks like this. So secant squared minus 1, that quantity, and then bring down the middle, this middle factor, our secant squared, and then bring down what will now be our differential. So secant x, tangent x, dx, right? Again, the one thing with these procedures is that there's very little in terms of surprise, right? I mean, because the roadmap has been laid out in front of you, right? It's just a matter of executing, knowing, what to look for and then which procedure to apply. So now what we're going to do is let u be equal to secant x. And this is going to work perfectly for us because du is secant x tangent x dx, right? So there we go. All of this now becomes our simple differential. We don't even have an extra constant to worry about. All of this becomes du. And then this secant squared is going to be u squared. And then this secant squared is also u squared. All right? So let's put that all together and now write down our new antiderivative in terms of u. So in parentheses here I have u squared minus 1, and then that's being multiplied by another u squared, and all of this is now my du. Right? But again, you'll notice the majority of these, once we convert it over to an integral in terms of u, before we actually integrate, we end up distributing some kind of power of u, right? It might be a fraction, as it was in the previous example, or it might just be positive integers. It could be negative integers. It could be anything. But just remember that here we have a product, so before we integrate it, we have to distribute that u squared and get u to the fourth minus u squared, and then that's what we integrate term by term. So in this case, our power rule gives me 1/5 u to the fifth minus 1/3 u to the third, and then plus c. And then of course, again, this being an indefinite integral, we want our final answer to be in terms of x. So take our secant and replace the u's right here. So this ends up being secant to the fifth power times 1/5, and then minus 1/3 times secant to the third power plus c, right? Again, once you identify that, okay, I know I have to do some procedure, I find the procedure in my notes or in the textbook or on some website, because they're all out there. These are no secrets. And then you apply it. The process, there's very little room for any element of surprise in these solutions, right? You just have to follow the map that's laid out in front of you. All right? Okay, so we got one more type to look at. And this one, there are two conditions. So then this is when now remember, we did the case where, in fact, let me go back up so I can refer to it. We did the case when n is even, right? And that's where we factors off the secant squared. Now we did the case where m is odd, and that's where we factor off a factor of tangent and secant. So what if m is even and n is odd, right? And that's the third case that we're going to deal with, and that's the one that involves the reduction formula for powers of secant. The scary thing, all right? Okay, so here's our third case. When m is even and, so both these have to be true, and n is odd, right? Because if both of these are not true, then one of the previous procedures would work, right? So when both of these are true, then this is where we have to use this third result. And okay, so this is where I was using my bullet. Here are my dashes. So basically what we're going to do is apply, or we're going to use this identity, the same one that we just used previously, that tangent squared is secant squared minus 1. So use this identity to reduce the integrand to powers of secant alone, to only, right? So reduce the integrand to only powers of secant. And guess what we're going to do with those powers of secant? We're going to then use our reduction formula to reduce those powers of secant. So use the reduction formula. And let me write the reduction formula down. This is where you have only powers of secant. So you have something like that. When you apply the reduction formula, you're going to end up getting 1 over n minus 1 times secant to the n minus 2 power times tangent of x, and then plus n minus 2 over n minus 1 times the integral of secant to the n minus 2 power with respect to x, right? So we will use this formula because all we're going to have are powers of secant. So use the reduction of formula, this one, to reduce the integrand, right? And if you have to do it repeatedly, you have to do it repeatedly. And what you can end up reducing this to, either, so reduce the integrand to either that integral, which we know how to do, or that integral, right? And yep, so that this is where that reduction formula for powers of secant will come in handy. All right, let's see an example of this one. All right, so suppose, so here's our example. Suppose we have the integral of tangent squared times secant x, right? The first procedure wouldn't work because the power of secant isn't even, and the second procedure won't work because the power of tangent is not odd, right? So you essentially eliminate those two, and then you're left with this third case, right? So what are we going to do? We're going to replace the tangent squared with secant squared minus 1. That way, the integrand will have only powers of secant, right? So let's do that. So we will have the product of secant squared x minus 1 times secant x. Distribute the secant x, and then this gives us secant to the third power minus secant x dx, right? Well, this one we know, right? This is the ln of the absolute value of secant x plus tangent x. That one we know. We did this in a previous video, but it's not something we tend to memorize unless you happen to use it a lot. So this one, we will apply our formula, right? So in other words, let's write it like this so that we see which one we're actually going to reduce and which one we already know the result for, right? So this one is the one to which we will apply our reduction formula. This one, we already know the result, right? Okay, so when we reduce secant cubed, or the integral of secant cubed, this is what it becomes. So in this case, my n is 3. So we will have 1 over 3 minus 1 times the secant of to the power 3 minus 2, so that's to the first power, so then this is of x, and then times our tangent, and then plus our 3 minus 2 over 3 minus 1 times the integral. Now again, when this, with an n equals 3, when we subtract 2, we're going to bring it down to a power of 1, right? So that's this part of it, and then we have to subtract this other integral. So minus the integral of secant x dx. So just to be clear, this integral is reduced to this one. You know, and it's almost strange when you say that it's been reduced because you look at it and it looks like it's gotten more complicated. But what the benefit of this is that this power is reduced to this power, right? Okay, so let's so once we have this, it's, you know, we can simplify. Let's see what we have. So this is 1/2 secant x, tangent x. And then in front here what we have is plus 1/2 the integral of secant x with respect to x. And then this is minus the integral, the same integral, right? And through properties of integrals, we have 1/2 here in front, a positive 1/2, and then we're subtracting 1. So again, these are not algebraic terms, but these are definitely like integrals because these are identical, right? So it's like you have 1/2 of one integral minus 1 of that same integral. So by taking 1/2 minus 1, we will get negative 1/2 of that integral, right? So let's do that. So this is 1/2 secant x tangent x, and then basically do 1/2 minus 1, so that's negative 1/2 of the integral, right? So basically just simplifying this expression, and now we have one integral to write down, and that antiderivative of secant x is the ln of the absolute value of secant x plus tangent x, and then we have our plus c, right? So that's where the reduction of the reduction formula for the powers of secant, it comes in very, very handy. All right, and that wraps up the procedures for powers of tangent and secant, right? Again, fairly straightforward, but it's not until you get into it and actually do this procedure yourself that you really start to see, for one, you see the differences between the two methods, and then you get a sense for, okay, which ones are going to end up with a substitution and which ones are going to end up requiring our reduction formula. So either way, have fun practicing. I'll see you in the next video.